All right, today we're going to talk about equilibrium expressions. Yesterday we talked about equilibrium expressions when we were talking about concentration, and we recall that that concentration is in molarity, and now we're going to talk about concentration in terms of pressure. Generally, it's in ATM. In fact, I don't think I've ever seen it in anything but ATM. If you know the concentration, the equilibrium expression, in terms of concentration, you can calculate equilibrium expression in terms of pressure as long as you know the gas law constant, because that's what you would need, and the temperature, and you recall that temperature must be in Kelvin, and you need to figure out the number of moles. And by that, the change in moles. It's the moles of the gas products minus the moles of the gas reactants. Literally, all you do is total the coefficients on the product side of those species that are gases minus the total of those on the reactant side. So here we go, calculating the value of Kp. So here's the reaction of the formation of nitrous silicon chloride. These two reactants form this product, and it was studied at 25 degrees C. At equilibrium, the values were found to be these pressures. Calculate Kp for this reaction. Well, Kp is the same as Kc. The only difference is to denote its pressure, we use parentheses instead of brackets. So we have the products, NOCl. We take the coefficient and make it the exponent over the reactants. That would be NO raised to the second power and Cl2. These are equilibrium values, so we just put them into the expression. Then we're going to do some math, and we will come up with a value for the equilibrium constant, and that value is, is 1920 is what I got, and using the number of significant figures in the problem 2, that would be 1.9 times 10 to the third. Alright, now we've been asked to take this Kp value and change it into Kc. So we recall that Kp is equal to Kc, and then we're going to take the gas law constant times the temperature and raise that to the change in moles. Well, Kp is 1.9 times 10 to the third. We are trying to find Kc. The gas law constant is 0.281. The temperature is 25 degrees C. That is 298 K. Let's look at the number of moles. There are 3 moles of reactants, 2 moles of products. It is products minus reactants, so this is being raised to the -1. So that's 1.9 times 10 to the third is equal to 0.0409. Divide both sides by 0.409 to get our Kc value. And I get that number to be 4.6 times 10 to the 4th. Alright, now let's talk about something called the reaction quotient. So far we've been very careful to say that the equilibrium expression only has values that are equilibrium concentrations. You cannot use a K expression with anything other than the values, be they pressure or concentration, that are found at equilibrium. Sometimes you don't know that they're at equilibrium, you have to test. For that, we use the reaction quotient. The reaction quotient is set up exactly like the equilibrium expression, where the reaction quotient Q are the products raised to their coefficients divided by the reactants raised to their coefficient. So what we're going to do is look at Q and K and make a judgment. If the value of Q is less than K, that means that the reaction, in this case this reaction, must make more products to reach equilibrium concentrations. So if Q is less than K, we need the forward reaction to go faster than the reverse reaction until we get to equilibrium. If Q equals K, then we have the concentrations that we were given are in fact equilibrium concentrations. If Q is bigger than K, then we need the reverse reaction to go faster until the concentrations equal the equilibrium concentrations. I think it's very easy to think of these problems as if they were on a on a number line. Here is an example of a problem using the number line. Okay, so we have the synthesis of ammonia at 500 degrees C. You're expected to know the synthesis of ammonia. It is a very famous process called the Haber process, where you take elemental nitrogen, react it with elemental hydrogen, and you make ammonia. When this reaction is balanced, it looks like this. The K expression for the Haber process would have NH3 raised to the second power over nitrogen times hydrogen cubed. So they give us these sets of reactants, and we're calling them Q because we don't know if they're equilibrium or not. So we take the products, divide by the reactants, and we come out with a number that is 1.25 times 10 to the 7th. The equilibrium constant for this is 6.0 times 10 to the negative 2nd. So K would be here, while Q would be way out here. So what that means is that in order for these concentrations to be equilibrium concentrations, this reaction must predominate. So it must move to the left or towards the reactants. We need to make more reactants. Likewise, we can find the same, using the same process here, we can find Q. And when we do this, you will see that Q is equal to K. And in this case, the concentrations that we were given are equilibrium concentrations. They are good to go. And for this last case, it says that we'll shift to the right. If you do the math here, I came out with a value that was 2. Given the concentrations, Q is equal to 2 times 10 to the negative 3rd. So that means that Q is smaller than K, so we need the forward reaction to predominate to make these shift right, to make these equilibrium concentrations.